Hi folks, in this episode of the microcontroller programming tutorial, I want to talk about how to get some pre-prepared binaries into the microcontrollers using some programmer software and programmer hardware. The previous episode I've showed you the various programmers and target boards I want to use, and today it's all about making the programmers do things by using the associated programmer software to make them what we want. If you remember the picture from before, we've taken a look at the target boards and the programmers in the previous episode, number 38 that is, and you hopefully have already installed the programmer software on your computer, where I used the Raspberry Pi, and downloaded the binary images which were in the tarball that I provided in the forum for episode 37. And today it's all about taking an existing binary image, run it through the programmer software, programmer hardware onto the board to make the LEDs on the various board do some sort of blinking that we can actually see, so we know that whatever we've tried to install has actually arrived in the microcontroller. That's the plan for today. And the first board I want to start with is the TI LaunchPad. Why the TI LaunchPad? Because it's actually the easiest one to use. The others aren't really difficult, but let's start with the simple one, go to the complex one. Makes it easier to understand what's important and what things you might actually watch out for if you want to use, I don't know, STM8 or something like that, whatever. Anyway, I've also pulled out, I've already had that for a while, little webcam. Put that on a travel tripod. I'm going to use that to show you what I have here on the bench, because that way you can actually see it while I do the desktop recording. It's easier than juggling with the one camera I have and mount it above the bench and then back on the tripod where you see me right now. And problem with this thing is it's full HD. It wasn't exactly the cheapest model I could find, but it still wants to focus on things way beyond the bench half the time. Sorry if you can still notice that, but you should be able to see the LEDs do some blinking. Okay, let's go with the TI LaunchPad. Okay, so here you see the TI LaunchPad, and the LEDs are blinking twice before pausing. We're going to change that in a moment. That's the whole idea, really. And if you followed the previous episodes, you should already have at least this BIVBlog 37-MCU-bootstrap-binaries and whatever timestamp on your computer. And if you've extracted that, you have this directory as well. So let's go there. This is the make file we used to set up the machine. So if you haven't done that yet, and you're preferably using some sort of Debian, Raspbian, whatever, you might actually go to that directory, say make, and then go for lengthy, well, I guess lunch break. On the Raspberry Pi it takes about an hour and a half to build everything, because mostly you have to build the stuff for the PICs from sources. And the Pi is not particularly fast when it comes to building a compiler. Now you see, I see otherwise three subdirectories: Atmel AVR, Microchip PIC, and TI MSP430. For the Launchpad, the obvious thing to do is to go for the TI MSP430 subdirectory, and in there you find 10 binaries, which are named Blink1 through 5-Launchpad-G2452 or 2553, which are the names of the two microcontrollers provided with the Launchpad pack or kit. What I want to do now is I want to install, let's say, Blink 5 on the Launchpad. And the tool we use for this is called MSP Debug. Why debug? Because the interface we're using to talk to the MSP430 is a combined programming and debugging interface. It's called SPI-by-wire. And basically, okay, let's give it a try. Just run MSP debug. You need to specify a driver. Try minus minus help for a list. Okay, whatever. And yeah, that gets us some information. So MSP debug options, driver command. We don't actually need any of these options, at least not necessarily, but we need a driver. Problem is, it doesn't say anything with regard to the available drivers that mentions a launchpad. So we should do at this point what we should have done before anyway, which is read a mend page. Yes, I know mend pages are for cowards, but cowards tend to live longer. So man MSP debug, and we search for launchpad. It supports the what launchpad what. Okay, that looks good. And here we have drivers. A driver name must be specified on the command line, blah blah blah. RF2500, connect to an easy 430-RF2500 launchpad or Kronos device. Okay, let's give it a go. Okay, that says something. Copyright and so on. Trying to open interface, initializing FET or FET is flash emulation tool, which is a strange historic name for programmer, but or debugger actually, but that's just the TI way to do it. Might as well explain at a later time where this all comes from when we do the debugging stuff. Set VCC 3000 millivolts. So we are actually providing the target board using the programmer. That doesn't always work. So sometimes we have to provide power externally, but in this case no external power is needed, which is pretty convenient. Configured for SPI-by-wire, that sounds good. Device ID OX2553, which looks suspiciously good. If you remember that we have a MSP430 G2553 in the board. And device MSP430 G2553/G2403, that looks good. Chip ID data. Available commands. Oh, this is a good one. We can run things. We can actually interface to GDB. That's nice. But all we need at this point is prog. So let's say prog. No such file or directory. That sounds reasonable. We haven't told it what we want to program. Let's say help prog. Prog file name. Now that was a surprise again. Let's try that. Prog blink 5-launchpad-g2553.elf. Erasing, programming, done. Okay, but our MSP430 launchpad board isn't doing anything. Why is that? Because this is a debugger, and with a debugger you explicitly have to start a program you want to debug. What we can do at the command line is say run, and then you see the LEDs start to blink. And that's 5 times before it's pausing, so that looks pretty good. We go back to the command line, do a Control-C, and the blinking stops again. Now, if you just exit the debugger, that basically means that we release the microcontroller from the debug interface, and at this point the LEDs start to blink again. So none of that is particularly difficult or exciting or complex. The only thing that's annoying is if we have to enter things interactively at the command line or within the MSP debug tool, then it's not much fun to do that from a makefile. And the one thing we can still do is we can actually pass additional commands from the command line of the shell, which is basically prog, and then we say blink 1. This is extra boring. Launchpad G2553.elf. This doesn't work. No such file or directory, because we have to pass every line within MSP debug as a single argument. So we have to put this into quotes or escape the blank between them. But if we do that, that looks good. Things work. And you see now the LEDs are just blinking once before pausing. Not exactly rocket science, right? It's pretty convenient. It's pretty simple. It's pretty, well, if you read the main page or watch a video telling you what to do, there's not much to it. Things might get a bit more complicated if we connect multiple launch pads to the same computer, because then we'd have to read a bit more on the main page to decide or to control which program gets loaded where. But not today, because we don't need it at this point. And I guess if you really wanted to, by now you should be pretty much set up to actually find out the rest in the main page if you really want to play around with this right now. That was the easy part. Next one is the Atmel AVR. And as I explained before, I'm going to use an Arduino as a target board using the ISP programming header, which is labeled ICSP on the Arduino, to program the microcontroller on there directly. This is a bit more, well, complicated, but not rocket science either. So here's our Arduino with my no-name programmer. And the reason why I actually put the programmer here as well is because of these two dip switches, because they control the voltage the programmer provides to the board. If I turn them both off, the Arduino shuts down. And I can control the voltages through them, setting it to, I think, 2.7, 3.3, and 5 volts. Both on means 5 volts, which is pretty much always good, because then you can run the Arduino at full speed and everything. And you see there's a power LED going on, and there's a blinking LED over there. And that blinking LED is a bit hard to see, especially if I make the video image smaller and go into the corner again. So what I have here is a 5mm LED plus series resistor plus a 2-pin male header plus some heat shrink, even transparent one. And if I just put that in the right, oh, that's not the one. Ah, there we go. Makes it much nicer to see. Okay, so back to your corner, and you see the LED blink just once. Good. Now let's go for the Atmel AVR subdirectory, and in there you see blink 1 through 5 again, and it's either for the Arduino Uno or it's for the ATtiny 13, 25, 45 or 85 blinking on pin PB0. That's because I've already used an ATtiny 13 and 25 at least on the breadboard and built the necessary binaries. So if you don't want to spend the money on the Arduino Uno but want to use things on a breadboard instead, you already find the binaries there. Just let me show you. So what I have here, oops, sorry, as an alternative is a bit of breadboard with an ATtiny. This should be an ATtiny 25 LED connected to pin PB0 and the necessary pull-up resistor on reset, decoupling capacitor. You can use that as well if you want. And well, yeah, we're going to stick with the Arduino here though. It's more convenient. Okay, let's put that back into its corner and reprogram it. Now, the tool we use to program an Atmel microcontroller in this case it's just a programming interface. The Arduinos, the bigger ones, have a JTAG interface which can be used for programming and debugging. But we're using the ISP interface, the in-system programming interface, which is only for programming really. And the tool to use for this is called AVR Dude. And there's what we need to know. It's AVR Dude and some optional options, except that -p partner is required. Specify AVR device. And what you should check in the main page or find in the main page is if you say AVR dude -p and then you have to quote that question mark, you get a list of all supported devices, and that includes the ATmega 328P, which is the one you have on the Atmel. And all you need to find that out is either good eyes or some kind of magnification glass. Okay, let's try that. What was it like? -p, ATmega 328P. You can use either the left-hand side or right-hand side of the list. Either one works, and it's not case sensitive. No programmer has been specified on the command line or the config file. Specify a programmer using the -c option and try again. Okay, AVR dude without anything, -c programmer. And yes, you can put things into a config file, but I am not too happy with that. I rather have things in a make file, which is something we'll take care of at a later time. But what we can say is -c programmer, and again we can say question mark to get a list of supported programmers. There are quite a few, quite a few, and with this no-name thing that I'm using, and pretty much all the no-name things, it's almost inevitably the STK 500 version 2 firmware. So it's STK 500 version 2. Now if you buy a no-name programmer, this is pretty much always the driver you need. But if you buy anything like that, make sure you check the documentation beforehand. You want the documentation to tell you at least what to use. And what you really want to avoid is that the programmer you buy actually requires some special proprietary programmer software, which of course is only available for Windows 95 and makes the entire thing pretty much useless, especially if you want to use it like me, using standard Unix tools and Unix-based toolchain and some mostly vendor and architecture independent tools all around. That's it. I've never seen any cheapie that was not STK 500 version 2 compatible. Okay. But there's still one more thing to do, because if you remember the previous episode where I showed you the real STK 500, that thing had a serial interface, an RS-232 interface. So we needed one of these USB to serial adapters. The no-name programmer I have here has that built in, but the operating system on the Pi, in my case, only sees there's a serial device. Doesn't know what it is. It could be a programmer. It could be a modem, if you still have anything like that. Even a VT100 terminal, or whatever else you connect using a serial interface. So we have a bit of a problem here. We need to tell AVR dude where to find the programmer, and basically to do that we have to give it the device name in /def, whatever, that we're using. And this is a real pain with USB-based devices, because there it depends on the order in which devices show up. So basically the order in which you plug them in or whatever. And every time you change anything like that, device names change. Real pain. You can work around that by fiddling with the UDEF, DEFFS, DEFD or whatever configuration your Unix uses, and make sure that certain devices with a certain serial number always get a specific name. But that's way beyond the scope of this video. Basically means I don't want to mess around with it right now. But what I want to show you is how to figure out the device name at the specific point and how to find that with the least possible hassle. Let's give it a look. Now the trick here is if we start with the disconnected device and do something like ls/dev and send that out to a file temp A. Then we do connect the device, wait a moment, and you don't want to be too fast here, and then do another ls/dev, send that to another file, and if we diff the two, we actually see, okay, there's a change of entry TTY-ACM0 has been added. So that's the name of our device. And yes, we could have done a demessage and probably should have seen, oh, this got really confused with plugging in and out devices. But sometimes you find something like this in demessages. That said, I know why I prefer to do this trick, listing the content of /dev. It works with all devices, even where the driver doesn't send that much output to demessage, and it just works more reliably. Anyway, where's our AVR dude? Well, there's our device, and we see if we invoke it, AVR device initialized and ready to accept instructions, reading, device signature, fuses, whatever, AVR dude done, thank you. Doesn't mean we've written anything, because that's where we really need the man page. And you have to read a couple things, and yeah, lots and lots and lots of stuff we don't need. But here's what you need. Perform a memory operation as indicated. Memtype field specifies the memory type to operate on. I probably have to tell you some things about address spaces and von Neumann and Harvard architecture things, but not right now. Anyway, what we want to write, no, it's not EEPROM, that's something different. It's Flash. No, it's not application either, because we're not using an ATX mega. It's just Flash. And the operation we want to do is read data from the specified file and write to the device memory. That's good. And yeah, we need to provide a file, as it says up here, -U, memtype, -up, and then -file name. So let's give it a try. -update, flash, write, and then it's blink 5, Arduino Uno.elf. Now, this blank shouldn't be here. It's just convenient to use the shell expansion. We run this, and we should see the LED blink 5 times before pausing. So that worked reasonably well. It's a bit more annoying because of this built-in FTDI or whatever chip in there, but otherwise, other than that, not exactly rocket science. So that was the no-name programmer, but we have two more, and they are slightly different. So for educational purposes and for completeness sake and whatever, I'm going to show you those just as well. So the next one to use is the Bus Pirate with my, I see that, if you can see that better, with my homegrown programming cable. And the first thing you probably notice is it doesn't power the Arduino. So I've got power from a regular USB wall-wart power supply thing, and we have to power the Arduino separately. Once we do that, it starts blinking again. Everything is fine. And we do pretty much, we should have actually done before. We should have done the previous trick about powering devices on and off. Let's see about that. There's the missing device. There's the connected device. And the diff shows, okay, there's device TTY USB 0. Good. Only thing we need to figure out, make that blink once again to be boring, change that to USB 0, and the programmer device. What should we use here? Let's try a question mark first. And good news, there's the bus pirate. Let's try that. And yes, we only get a single blink. So the only difference between the no-name programmer and the bus pirate, aside from that we need to specify a different programmer type is, and a different device name, is that we actually have to power the Arduino board externally. Not a big deal if you know it. Just something you want to be aware of. Okay, one more thing to go, and that's where things get nice. The AVR Dragon board. This one. Okay. It's not going to be that hard. The big difference here is that this is a real USB device, so it's not with this serial adapter interface in between, which means we just specify the device slightly differently. No rocket science. We're done in 2 minutes, so bear with me. Like the bus pirate, we need to power the Arduino board externally. There are some power headers here on the AVR Dragon which we could connect separately to the Arduino, but the other cable is already in, so why bother? And what do we need to do? Okay, let's take a look at the list of programmers again. There's Dragon debug wire mode, high voltage serial programming mode, ISP mode, JTAG mode, PDI, PP, whatever. The one we need is this, Dragon ISP. And you can find that out in the main page if you want. Basically, what you do is device, you just say USB. And programmer, Dragon ISP. And we make our Arduino blink, let's say 3 times. So you see, programming works, LED is blinking 3 times, and well, that's all there is to it. It's a bit more complicated. You have to be a bit careful about power supply. You have to specify the right device name. There are different driver names. But other than that, no rocket science. It's just reading main pages. And what we're going to do in the, I guess, next episode is put everything into a makefile so we can forget about it until we actually have to change things there. And then have things prepared in such a way that it's easy and straightforward to change. So, for example, for a different programmer. What's left is my eternal favorite PIC Debug Express board. And yes, this is going to get a bit more painful. Now, the programs we've used so far, MSP Debug and AVR Dude, you can install that from your usual Linux distribution. They're pretty much always there. And no big deal. For these, you have to build things from source, both for the programming part as well as for the compiler. And that's why I've got the makefile for. If you haven't done so yet, well, get it going. You can actually say, with a makefile, you can say make programmers, and it'll just build the programmer software, which is for what we need right now. Builds reasonably fast. Building the compiler as well, as I said, takes about an hour and a half. Anyway, let's get over this and set this up as well. One of the things that I haven't completely figured out just yet is apparently it is possible to power the board from the programmer, but it depends on some weird things. While we are programming things, we don't need to power it externally, but afterwards we do. And with that, we might actually leave the power connector on as is. And yes, by now I've soldered a 2-pin header in here to power the board. And you see, It's going through the usual blinking routine. You already know the drill by now. The programmer is connected, and now we go to the directory with the Microchip PIC stuff. There you see 5 files, blink 1 through 5 for debug express. Haven't got any other targets right now. I'm still waiting for some delivery that DHL screwed up. But this is all we want to program. And the tool to use is called PK2 command. PK2 command. And this is a bit of a bitch. Why is that? Because it's written by people who are not really familiar with the way Unix things work. So the options are case insensitive. And we can say something like PIC 16F887, which is the microcontroller on the board. But that's not going to work. We're not going to get a complaint right now. It just, well, we get first error PK2 device file.dat not found. And for that to work, we need to specify -b, and then it's user share PK2 for PK2, which is strange because if you install sources from not distribution, these things should go to user local whatever, and pretty much everything else goes there, but not this directory. And the second thing, of course, is if there is a default place which is basically used through the build installation process, it should have been installed in the program as a default setting. It's a pain. And this is not going to work because it says no path given. Why is that? Because we put a blank here. This is strange. Operation succeeded. Doesn't even know what target we're talking about because we have to remove the blank here as well. But if we say -m, it's probably for modify, but I don't know. And then in a separate option -f, and then the file name, let's say blink1, and again no blank here, then we can actually program the device. Some things are happening. Program succeeded, operation succeeded, but no blinking. Why is that? Because for this to work, we have to disconnect the programmer. And then we see the board blink. Just once. And just for the fun of it, reconnect the programmer. Say blink 5. Run things again. Disconnect the programmer, and we see the LEDs blink 5 times before pausing. I'm decidedly not happy with this PK2 command thing, but the PK2 programmer actually has a nice feature which we haven't needed and for that reason haven't used. You can give these things names. You choose whatever name, and then you can actually, rather than provide them a device name that might actually change all the time, you just say talk the PK2 that is named so-and-so. That's cool. Seriously, that's cool. And yeah, only problems are the PK2 doesn't support all, especially the latest PIC microcontrollers, which is a pain. You need to disconnect it. The PK2 command thing is, it doesn't feel right for a Unixer. Put it like this. There's no main page. That's always a big minus in my eyes. But if we choose the proper kind of microcontroller, it basically does the job. So I'm not going to complain. I'm going to keep the PIC stuff around until I really get stuck with them. And for now, things are reasonably fine. Okay. So much about the programs for today. I hope you enjoyed this. If you have questions, comments, requests, whatever, as usual, come to the forum at www.stepladder-at.com/bivblog/39 this time, and hopefully see you again soon when we take care of the compilers. Bye.